In this video, we're going to take a look at some additional descriptions we can add onto this notion of what is a vector field. So here's our starting definition. If f is a scalar function of 2 or 3 variables, so that means that it's a function that when I go ahead and I plug in multiple variables, I spit back only one variable at the end. So this is a function like what we saw in chapter 3 when we had surfaces and landscapes. But if it's a function of 2 or 3 variables, then gradient of f as a vector could then be considered a gradient vector field. Like the gradient itself is a formula that takes in x comma y comma z and spits back a vector. So it operates just like the capital F's that we've been seeing. So here's another definition. A vector field f is called a conservative vector field if it is the gradient of some scalar function f. So mathematically, this means that there would have to exist a scalar function f so that when I took the gradient of it, it would create the formula for that capital F. In this situation, we say that little f is called a potential function for capital F. Now we're going to be dealing with this notion of conservative vector fields for quite some time here in chapter 5. So it's an important idea to recognize right away. Let's take a look here at example 3 to see how we can put these definitions to use right away. So first, I want to prove that this function is indeed a conservative vector field. I can see that it creates a vector field, right? I know that I plug in x comma y and I get back a bunch of different vectors. But if it's conservative, then that means that we would have to find some function out there in the world that when I take its gradient, this is what it would spit out. So I'll say that we want to find a function f of xy so that the gradient of little f equals capital F. If I can do this, then I know that my capital F is conservative. Well, maybe with just a little bit of tinkering around, you might be able to come up with something. I'd ask you to go ahead and try to pause the video here to see if you could come up with a function whose gradient comes out as exactly x comma y. So pause the video really quick and then you can hit play again when you want to see the answer. All right, so here's the answer that I would have. I would say, let's consider the function f of xy that's just equal to a half x squared plus a half y squared. Notice, if I take its gradient, the gradient of little f is automatically going to be equal to x comma y. And so it does equal exactly what the capital F was equal to. So capital F is conservative automatically. Remember though, we also, just as a side note, we call little f a potential function for capital F. Okay, so this here is actually a very simple thing to do at the moment. The question that I might have down here at the bottom is this the only function that would have worked in the above proof? Well, you could pause again to try to think about that. Could you come up with any other function that might have also been able to produce the same gradient? Well, actually, the answer to this is definitely no, this is not the only function, because you could easily imagine going up to what I have up above and like maybe just adding a number, right? And so automatically, if you can add a number and get the same gradient, you could definitely say there are infinitely many functions that could make this. So that's kind of an interesting thing to note. One other note that I have down here at the bottom is that at the moment, we don't really have any other ways of determining whether a vector field is conservative. We kind of at the moment have to look for this potential function. And so we're going to have to do a lot of guessing and checking until we get to section 5.3. In there, we'll actually talk about some more advanced ways that we can determine whether a vector field is conservative or not conservative. In the next video, we'll take a look at example number 4.